All right, if you're gearing up for your OEN 351 exam, you have come to the right place. We are about to tackle everything you need to know for Unit 2, Conveyance from the Source. My goal here is to get you completely prepped and ready to ace this, so let's just jump right in.
So here's how we're going to break it down. We're going to follow the water's journey from the source all the way to the tap. We'll look at intake structures, the pipes that carry it, the physics of how it flows, the network design, and finally, all the little gadgets that keep the system running. Following this path is a great way to remember the whole process for your exam.
Okay, first stop on our journey, the source. The very first challenge for any engineer is how do you get the water out of the river or lake safely? Well, that's where intake structures come in.
So what is an intake structure? It's basically the gateway for the entire water supply system. Think of it like a bouncer at a club. Its main job is to let the clean water in and keep all the trouble, debris, fish, excessive silt out. It's a super important first step. Now, where you put this thing is a huge deal. It's not as simple as just dropping it in the water. You've got to think about a bunch of factors. You want it close to the treatment plant to save money on pipes, right? But you also want it where the water is cleanest. And you need to make sure it won't run dry in a drought or get washed away in a flood. And definitely not downstream from a sewage plant. It's a real balancing act, a classic engineering problem.
Okay, so there are a few different types of intakes you could build, depending on if you're drawing from a river, a lake, or a canal. But for your exam, the one you really need to know about is the intake tower. It's the most common and interesting one, so let's focus in on that.
And here it is, a guaranteed favorite for exam questions. The difference between a wet intake tower and a dry intake tower. It's actually pretty simple when you break it down. A wet tower is, well, wet inside. The water from the river fills up the tower itself before going into the pipes. Think of it like a big concrete well. A dry tower, on the other hand, is just a dry shaft that gives workers access to the valves on the pipes. Water goes straight into the pipes, not into the tower. That's the key difference you got to remember.
All right, mission accomplished on collecting the water. But now we've got a new problem. Moving it, sometimes for hundreds of miles. So let's talk about the highways of the water world. Pipes and conduits. Before we get into all the different kinds of pipes, let's think about what we're even looking for. What makes a good pipe? Well, it's got to be tough, right? Able to handle pressure from the inside and the outside. It can't be a pain to install. It needs to last for decades. Crucially, it shouldn't mess with the water quality. And, of course, it has to be affordable. This is basically the job description for a pipe.
Okay, this table is gold for studying. Seriously, it lays out the pros and cons of all the major pipe materials. You see, there's no magic perfect pipe. It's all about trade-offs. Take cast iron, for example. It's super strong and can last a century, but it's brittle and heavy. Then you've got something modern like PVC. It's light, cheap, and won't rust, but it doesn't handle heat well. The big takeaway here is that an engineer's choice depends entirely on the specific situation. The pressure, the budget, everything.
Rust, corrosion. It's the #1 enemy of any pipeline. It's a constant battle. So how do we fight it? Well, engineers use a whole arsenal of weapons. It starts with picking the right material in the first place. Then, they add protective shields, like coatings of cement or tar. They even use some cool electrical tricks with something called cathodic protection. And finally, they can treat the water itself to make it less aggressive. It's a four-pronged attack to keep the pipes healthy for as long as possible.
Okay, deep breaths. We're moving into the physics and math part now, water hydraulics. But don't stress, you're not going to be doing complex calculations on your exam. The key here is to understand the concepts behind the formulas and know what the different parts mean. Let's do this.
So the first big concept is head loss. What is it? Imagine water is carrying a backpack full of energy when it starts its journey. As it flows through the pipe, friction with the pipe walls is like a little thief that keeps stealing bits of that energy. That loss of energy is what we call head loss. And it's a huge deal because if you lose too much energy, by the time the water gets to its destination, it won't have enough pressure to even come out of the tap.
All right, here's one of the big name formulas for figuring out head loss, Darcy-Weisbach. Now look at it. Looks intimidating, right? Don't panic. You just need to be able to recognize it and know what the letters stand for. HF is the head loss we're trying to find. F is the friction factor, how rough the pipe is. L is length, V is velocity, and D is the pipe's diameter. Just know the players in the equation, that's it.
And here's another one they use, the Hazen-Williams formula. It's just a different way to calculate the same thing.
The most important letter to notice here is C. That C is a coefficient that represents how smooth the pipe is. A super smooth plastic pipe will have a high C value. An old, rough, corroded pipe, a very low C value. Higher C means less friction, which means the water flows faster. Simple as that.
So, we've gotten the water from the source, we put it in a pipe, and we know how to calculate its energy loss. Now for the final leg of the journey, getting it to everyone's homes. This is where we design the distribution system, the web of smaller pipes that looks like a city's roadmap.
Another classic comparison for your exam. There are two main ways to lay out this pipe network. First is the dead-end system. It looks just like a tree, a big trunk main with smaller branches shooting off. The problem, the water at the end of a branch has nowhere to go, so it can get stagnant. The other way is the gridiron system. This looks like a city street grid. Every pipe is connected. This is way better because water is always circulating, and if one pipe breaks, water can just find another route.
And this table just nails it down. For your exam, pay close attention to the columns. The big problems with the dead-end system: stagnant water, and if a pipe breaks, everyone downstream loses water. The big wins for the gridiron system: better water quality and much more reliability during repairs or fires. Know those points cold.
Now let's talk about when the water is supplied. In a perfect world, you have a continuous system, water 24/7. It's hygienic, it's great for fighting fires, but in many places, because of water scarcity, they use an intermittent system where water only comes on for a few hours a day. This is actually pretty dangerous. Why? Because when the pipes are empty, they can actually act like a straw and suck in contaminated groundwater from any little crack or bad joint. That's a massive public health risk you just don't get with a system that's always full and pressurized.
Okay, last major section. We're talking about appurtenances. It's a fancy engineering word, but all it means is all the other stuff in the network that isn't a pipe. We're talking about the valves, the hydrants, the meters, all the gadgets and controls that make the system actually work. Think of them as the brains and controls of the whole operation.
First up, the sluice valve, or gate valve. This is your basic on-off switch. Its job is to completely stop the flow. They put these all over the network so that if there's a leak on one street, they don't have to shut down the water for the entire town. They can just isolate that one little section, like flipping a circuit breaker for one room instead of the whole house.
Next, we've got the check valve, also called a non-return valve. This thing is super simple, but incredibly important. It's a one-way door for water. Water can flow forward, but it can't flow backward. Why do you need this? Well, imagine you have a pump pushing water up a hill. If that pump suddenly stops, all that water is going to want to rush back down. The check valve slams shut and stops it, protecting the pump from being spun backward and destroyed.
This one's a little surprising. You'd think it's just water in the pipes, but air can be a huge problem. Air gets trapped and collects at the highest points in a pipeline, forming a big bubble. This bubble, called an airlock, can literally stop the flow of water dead in its tracks. So what do? You install air valves at all these high points, and their only job is to automatically let that trapped air escape, kind of like burping the pipeline to keep things flowing.
And to round it out, a few more key players. At the lowest points of the network, you have drain valves to flush out all the sand and gunk that settles. You've got fire hydrants, which we all know, for giving firefighters a high-pressure water source. And of course, water meters, which measure how much water you're actually using. Every single one has a really specific and important job.
Okay, so none of this water moves on its own, right? We need pumps to provide the muscle. But picking a pump isn't like just grabbing one off the shelf. It's a huge decision. You have to think about, can it move enough water? Can it push it high enough? Is it efficient, or is it going to rack up a huge electricity bill? Is it reliable? And what about the cost, not just to buy it, but to maintain it for the next 20 years? It's a major balancing act.
And that's the whole journey, from the river to the tap. We've covered a ton of ground here. As you study for your exam, try not to just memorize the individual parts. Think about how they all connect. Answering this question on the screen is a great way to do that, to see the whole system. What do you think is the most critical link in this entire chain? Really think about it. All right, you've got this. Good luck on the exam.